Composing the backdrop of Salt Lake City, Provo, Ogden, and other communities in north-central Utah, the Wasatch Range is an absolutely stunning mountain range that offers some of the best outdoor recreation around, including hiking, rock climbing, winter sports, and so much more. Running for roughly 200 miles from Soda Point in southern Idaho down to the town of Nephi in north-central Utah, the Wasatch crests at 11,929 feet on the summit of Mount Nebo and is one of the most dramatic ranges in terms of relief in the United States, making the drive on I-15 all the more interesting. Recording billions of years of geologic history and having been uplifted over the last 17 million years, the range is still growing today and is an excellent location to witness the eventful geology of Utah firsthand. But how are these beautiful mountains formed? What are the geological processes that shaped this iconic range? Why does this mountain range even exist? In this episode of Solomon's Outdoor Adventures, we're going to answer all of that and more as we explore the fascinating geology of the Wasatch Range. Let's start by talking rocks. The story of the Wasatch Range begins 1.8 billion years ago during the mid-Precambrian era, when the oldest rocks that outcrop in the range were formed. These gneisses, schists, and migmatites of the Farmington Canyon complex and the Little Willow Formation are a part of the core of rocks that assembled ancient North America. During this time, western Utah was on the edge of the ancient North American continent, and these high-grade metamorphic rocks record the ancient history of how this part of North America was assembled. You see, the sediments that these metamorphic rocks are composed of date back 2.8 to 3.6 billion years, and were derived from the core of the ancient North American craton. In geology, a craton is just a fancy word for the main nucleus of a continent. The Farmington Canyon complex and Little Willow formations were metamorphosed between 1.8 and 1.6 billion years ago, when the Grouse Creek block was stitched onto the western edge of ancient North America. As the Grouse Creek block accreted, what would become the Farmington Canyon complex and Little Willow formations were caught between the Wyoming Craton to the east and the Grouse Creek block to the west, metamorphosed as they were sandwiched between these two blocks of crust. The Farmington Canyon complex is widespread in the Wasatch north of Salt Lake City, specifically east of Ogden, Farmington, Layton, and Willard Bay. The Little Willow Formation, on the other hand, can be found in both Little and Big Cottonwood Canyons, just east of Sandy and Cottonwood Heights. There is some evidence that may suggest that the Farmington Canyon complex was initially metamorphosed roughly 2.6 to 2.4 billion years ago, well before the aforementioned period of metamorphism attributed to the accretion of the Grouse Creek block, as some zircons from the complex contain dates in this age range. With that being said, though, mainstream evidence today points to intense metamorphism of the Farmington Canyon complex commencing 1.8 to 1.6 billion years ago. Following this period of metamorphism that built the Wasatch's oldest rocks, what would become northern Utah underwent a roughly 700 million year long period of rifting, becoming what is known in geology as a passive margin, an area where continental crust phases into oceanic crust in the absence of a plate boundary, much like the Atlantic coast of North America today. The area became submerged under a shallow sea roughly 850 million years ago, when quartzites, slates, argillites, and shales of the Big Cottonwood Formation were deposited in shoreline environments in what would become Little and Big Cottonwood Canyons. The area remained submerged under a shallow sea for roughly 700 million years after the deposition of the Big Cottonwood Formation, until the onset of the Sevier orogeny in the area roughly 160 million years ago during the late Jurassic period. This extensive period of western North America being under the ocean is documented extremely well in the Wasatch Range, as much of the Wasatch's rocks are sedimentary rocks of shallow marine origin. Some notable Paleozoic-aged sedimentary suites in the Wasatch that record these shallow marine environments include the Tintic Quartzite, Ochre Formation, Deseret Limestone, Weber Sandstone, and thick suites of Mississippian and Pennsylvanian aged limestones and dolastones. Some of these units are thick, and I mean thick AF. The Ochre Formation, for example, has an estimated thickness of up to 30,000 feet. These thick Paleozoic sedimentary sequences are prevalent throughout much of the range, but some places to really see these units in all of their glory include on Mount Timpanogos near Provo, Mount Nebo in the south part of the range, and in the Bear River Range near Logan in the northern section of the Wasatch Range. During the Mesozoic era immediately before the onset of the Sevier orogeny, northern Utah was under a very shallow sea, and in some instances, in beach, tidal flat, and desert environments. This is recorded quite well in the early Mesozoic strata of the region, including in the Triassic to Jurassic aged Nugget Sandstone that outcrops in Parley's Canyon just east of downtown Salt Lake City. The Nugget Sandstone is northern Utah's equivalent of the Four Corners region's Navajo Sandstone, recording a vast sand dune desert environment similar to today's Sahara Desert. The youngest rocks that outcrop in the Wasatch Range are Oligocene-aged intrusive rocks of the Little Cottonwood Stock that are ubiquitous in Little Cottonwood Canyon just east of Sandy. Lone Peak, Pfeifferhorn, and White Baldy, three peaks that compose a massif just south of Little Cottonwood Canyon and east of Draper, are entirely composed of these intrusive igneous rocks. These quartz monzonite plutons date back 32 to 26 million years and are associated with copper and other metal deposits. Copper, gold, silver, molybdenum, zinc, lead, and other metals were deposited where the pluton intruded into pre-existing sedimentary rocks, and both Little and Big Cottonwood Canyons were extensively mined and quarried in the 1800s and early 1900s. Several abandoned mines can be found in the area, and in fact, the Little Cottonwood Pluton itself was widely quarried to build Mormon temples in the region. The Bingham Canyon mine lies immediately across the Salt Lake Valley from Little Cottonwood Canyon, and mineralization of the Bingham Canyon deposit was generated by an igneous pluton in the Ochre Mountains of similar age and lithology to the Little Cottonwood Stock in the Wasatch Range. This porphyritic pluton intruded the Ochre Formation, depositing insane amounts of copper, gold, molybdenum, and tellurium, eventually leading to the development of the world's deepest open pit mine. Both the porphyritic pluton of the Bingham Canyon deposit and the Little Cottonwood Stock owe their genesis to a large volcanic flare-up that occurred in western Utah and throughout Nevada during the mid-Cenozoic era, 45 to 25 million years ago. In fact, the vast Carlin-type gold deposits of northern Nevada also likely attribute their genesis to this igneous flare-up. To learn more about Nevada's Carlin-type gold deposits, click on this video. The Wasatch Range has a relatively complex uplift history, occurring in three main episodes. The first during the Sevier orogeny, the second during the Laramide orogeny, and the third during Basin and Range crustal extension. The Sevier orogeny was what initially began uplifting the Wasatch Range, and it occurred during the late Jurassic until the beginning of the Paleogene period, from about 160 to 50 million years ago. It was formed as the Farallon Plate was subducting beneath the North American Plate, the same tectonic regime that generated the Sierra Nevada magmatic arc in what would become California, except in what would become north-central Utah, things were a little different. A thin-skinned fold and thrust belt was generated east of the Sierra Nevada magmatic arc during the Sevier orogeny, and this belt is known as the Sevier fold and thrust belt. A thin-skinned fold and thrust belt is a type of mountain chain generated by compressive tectonic forces that fold and thrust sedimentary layers, causing them to detach from underlying basement rock and stack up in a series of thrust sheets. Detachment occurs along décollements, or detachment faults, and deformation of this style only involves topmost sedimentary rocks of the Earth's crust. This tends to occur in areas where very thick sedimentary units are involved, and given the fact that Utah was under a shallow sea for almost 700 million years prior to the onset of the Sevier orogeny, those units were more than thick enough to undergo thrusting. In the Wasatch Range, the Sevier orogeny generated a litany of geological structures, including countless thrust faults involving pre-existing sedimentary units, as well as synclines and anticlines throughout the range. Thrust faults occur due to compressive forces and involve the thrusting of one rock layer over another. Synclines and anticlines are geological structures that occur when sedimentary units have been folded due to compressive forces. Synclines are roughly U-shaped structures of sedimentary rocks, while anticlines are roughly A-shaped sedimentary structures. Throughout the Wasatch, examples of these severe originating structures can be seen all over the range, but the best visual evidence of the Sevier orogeny, in my opinion, can be seen at the mouth of Parley's Canyon immediately east of Salt Lake City, particularly where I-80 and I-215 come together. Here, a major structure that dates back to the Sevier orogeny occurs, the northeast trending Parley's Canyon syncline, which runs from the western foot of the range at the mouth of Parley's Canyon to the eastern foot of the range northeast of Echo. Mesozoic rocks are highly folded, and driving I-80 from Salt Lake City up to Park City will take you through a treasure trove of sedimentary units that were tightly folded into the Parley's Canyon syncline during the Sevier orogeny. More striking evidence of the Sevier orogeny can be seen in the southern portion of the range, particularly near Mount Timpanogos, Mount Nebo, and in Provo Canyon off of Highway 189. Folds and thrust faults related to the Sevier orogeny, such as the Charleston-Nebo thrust, are commonplace in this portion of the range. Evidence of the Sevier orogeny is not restricted to the Wasatch Range, as it occurs throughout the entirety of western Utah and eastern Nevada, all the way up to Canada. While we can say that the Wasatch began their uplift history during the Sevier orogeny, the Sevier orogeny did not exclusively create the Wasatch Range. What would become the Wasatch were simply a part of a larger mountain range during the Cretaceous called the Sevier Fold and Thrust Belt. The second phase of uplift history in the Wasatch Range was attributed to the Laramide orogeny, a mountain-building event that transpired in western North America roughly 70 to 34 million years ago, and was largely responsible for uplifting the majority of the Rocky Mountains and Colorado Plateau. Though the Laramide orogeny did have a major impact on the Wasatch Range, it was not as widespread throughout the range as the Sevier orogeny was, as it mainly affected the central Wasatch Range. The Laramide orogeny was responsible for exhuming deeply buried rock near Little and Big Cottonwood canyons, including the Little Willow Formation. These tectonics generated a structure known as the Cottonwood Anticline, which dominates the Wasatch Range from east of Mill Creek to east of Alpine. The Cottonwood Anticline features late Precambrian and early Cambrian layers dipping around a core of Precambrian basement that was exhumed to the surface of the central Wasatch, exposed from Box Elder Peak to Mount Raymond. Just south of Parley's Canyon, Mount Raymond showcases excellent evidence of the Cottonwood Anticline, as the entire northern half of the mountain is very steeply dipped, folded due to the compressive tectonics of the aforementioned Laramide orogeny. The Wasatch Range as we know it today specifically began being uplifted roughly 17 million years ago, during the Miocene epoch. This was when widespread rifting and crustal extension associated with the basin and range commenced in western Utah. Considered both a part of the Basin and Range and the Rocky Mountains, the Wasatch Range is really just a transition zone between the two geological provinces. It's composed of the westernmost stable block of North American crust at this latitude, and because of that, it's been uplifted into the mountain range that it is today. Much of the energy generated from crustal extension of the unstable basin and range to the west is transferred to the edge of the stable crust that lies beneath the Wasatch Range. This energy transfer generates a highly active fault system on the western foot of the Wasatch that works tirelessly to uplift the range, generating earthquakes as the mountain range grows. Bounding the western escarpment of the Wasatch Range, the eponymous Wasatch Fault is a 240-mile-long fault system that poses tremendous seismic risk to the Wasatch Front as it continues to uplift the range today. The Wasatch Range is currently being uplifted at a rate of about 0.8 to 1.2 millimeters per year, which may sound pretty slow, but is actually pretty fast geologically speaking. Because the range is being uplifted faster than it's being eroded, it's considered to be quote-unquote growing. These tectonic processes involving the Wasatch Fault have more or less continuously transpired for the last 17 million years, uplifting the Wasatch to its current height of 11,929 feet above sea level. According to the USGS, highly damaging earthquakes of magnitude 6.8 or greater occur on the fault every 300 to 400 years, the last major one occurring near Nephi roughly 300 years ago. The Wasatch Fault is split into 10 segments, and of the 5 central segments between Nephi and Brigham City, at least 26 earthquakes of magnitude 6.5 or greater have occurred within the last 6,500 years. The strongest possible earthquake that could hit the Wasatch Fault, according to the USGS, would be a magnitude 7.5 earthquake that would be highly damaging to wherever it hits in the Wasatch Front. According to seismologists at the University of Utah, there's a 57% chance that the Wasatch Fault experiences an earthquake of magnitude 6.0 or greater within the next 50 years. Due to the steep topography of the Wasatch Range, shaking is not the only hazard that would be posed in the event of a large Wasatch Fault earthquake. Devastating landslides pose a serious risk to communities, as there is no shortage of evidence of great landslides that have occurred during past earthquakes in the area. An exceptional locality to see the Wasatch Fault firsthand is at G.K. Gilbert Geologic View Park at the mouth of Little Cottonwood Canyon. Here, scarps of the Wasatch Fault are highly visible and ubiquitous, recording up to 40 feet of vertical offset from recent earthquakes on the fault. The park's namesake, G.K. Gilbert, was a geologist that contributed a tremendous amount of knowledge to the geology of Utah in the late 1800s. Though no glaciers remain in the Wasatch Range today, the range was heavily glaciated during the last ice age, home to at least 60 large glaciers as recently as 13,000 years ago. Evidence of these glaciers abounds in the range, as glacial landforms such as cirques, moraines, U-shaped valleys, and others are numerous. Little Cottonwood Canyon, for instance, is a textbook example of a U-shaped valley, a valley that was carved into a U shape due to glaciation. Not only were the mountains glaciated during the last ice age, the West Desert was filled by a massive lake known as Lake Bonneville. Lake Bonneville was huge, stretching from the Wasatch Front west to Nevada, down south past Milford, and north to Idaho, encompassing over 20,000 square miles. The Great Salt Lake is a shrinking remnant of Lake Bonneville that surface elevation is at 4,206 feet, but at its height, Lake Bonneville had a surface elevation of 5,090 feet, lapping all the way up to the slopes of the Wasatch. This high stand is known as the Bonneville level and occurred 16,000 to 14,500 years ago, when the lake had a maximum depth of 980 feet. Past shoreline levels of Lake Bonneville are visible today, as terraces on the lower slopes of the Wasatch Range, Stansbury Range, Oquirrh Mountains, Wellsville Mountains, and other ranges in the area record where lake levels used to be. Terraces from Lake Bonneville's high stand on the lower slopes of the Wasatch are ubiquitous throughout the western slopes of the range, but perhaps the best location to really see them in action is in the section of the range immediately north of Salt Lake City, from Bountiful through Farmington up to Ogden. You can really see Lake Bonneville's terraces on the lower slopes of the range here. It's actually really cool to look at. The Wasatch Range is an absolutely stunning mountain range that records the regional geology of Utah and western North America beautifully. Hopefully you learned a thing or two about them in this installment of Solomon's Outdoor Adventures and enjoyed doing so. If you liked the video, please consider liking and commenting on it, as well as subscribing to my channel if you haven't already, as it really helps me to get more content like this out to y'all. Thanks for watching, and as always, peace! Thank you for tuning in to another episode of Solomon's Outdoor Adventures. If you enjoy content like this, please like the video and subscribe to the channel, and check out some of our other adventures right here. As always guys, thanks again and peace!